you get a gold star for today, Kyle.
Can I just get like $2 so I can ask you questions?
$2? Man, you make more money than I do.
No, that's not what I'm saying. I'm saying can I get
Oh, okay, credit. Okay, yeah, there we go. All right. So before we can start talking about work that's done by varying forces, by varying force I mean a force that might start at 0 and increase according to some function to some other value, right? As it's doing work on an object continuously, and that object continuously undergoes a displacement. It might sound pretty complicated. It is kind of complicated. Right? We know that the equation for work, on our formula sheets says that the work done on an object is equal to the force on that object times the object's resulting displacement times the cosine of the angle between those two guys. So again, the work, or W is work, F is force, D is displacement, and again, I like using delta X or delta Y there, or in general delta R for general displacement vector, but it's D on the formula sheet. Theta is the angle between the force and the displacement vectors. So the theta, the cosine of the angle, is what takes care of your vector stuff. So you don't have to worry about the vectors when you're dealing with this F and D. So when you're dealing with those guys, remember to just use the magnitudes. The deal here, and this is the limitation of this equation, is that force F must be constant, right? The force F cannot change. If the force F changes, then this equation breaks down and doesn't work anymore. Does that make sense? You understand why that is? When you have an algebraic equation that says this equals this times this, you're assuming those things are constant. Yes, you can change one and see how something else changes as well, but if I want to know the total amount of work done by a force that varies, this equation is no bueno. Can't use it. Okay.
Even if it's constant?
What's that?
Like even if the force applied is at a constant acceleration?
If the force is a constant force, then yes, we can use it.
No, like I'm talking about like if it constantly increases.
If it constantly increases, this doesn't work. No, we have to use another technique. That's what we're going to learn today. So if it increases constantly, we can, with our knowledge of algebra, we'll be able to handle that. But if it changes according to some curvy function, then we actually can't do that. But we will talk about that a little bit today. So realize that's why, you just need to know that, because if you notice on the front page of your notes, you got a graph that actually indicates a changing force. So the way that we can deal with forces that change and the work done by them is graphical. We have to deal with graphs. You remember at the beginning of the year, years ago, when you're small children, and we learned about motion graphs, we can get information from those graphs by either determining slopes or determining areas. Take a velocity time graph, for instance. We can find the slope of velocity time graph tells us acceleration. The area under the velocity time graph told us displacement, right? So we can get information like that from graphs. Different graphs can give you different information, right? We're not always going to plot things with respect to time. We're actually, the graph we talk about today is not going to have time on the horizontal axis. So to illustrate this concept here, I got a force, and let me put it at an angle. I got a force that's going to be exerted on this sphere. I've turned friction off because if friction is on, then it gets more complicated. We want to start pretty basic. But I have a force that's going to act on this object, and the object is going to move. It's going to accelerate. It's going to cover a certain distance. Please understand that when we do the work equation, there's no acceleration in there. It doesn't matter if the object is accelerating or moving at constant speed or not. It doesn't matter. What matters is the actual force and the undergoing the displacement, regardless of whether it accelerates or not. That's one of the useful things about work and energy, is that you kind of can just forget about other things. That if you're using Newton's laws, you definitely can't. Okay. So I'm going to plot the force, not versus time, but versus displacement. So I plot the force and the position x. And I think I did this. Don't want the x component of the force, I just want the magnitude of the force. And then if it is a constant force, then if I plot then the force, the component of the force doing work. Please understand that too. I got a force at an angle. That force I can break into components. This component does work. This component does not. Cool with that? Just like the normal force doesn't do work, it's perpendicular to the direction of the displacement. The weight force doesn't do work, it's perpendicular to the displacement. So I hit play here, and I get what I... Okay, yeah, I don't know why that happened. Let's just start it again. Let's start it from here. There's limitations to algodo this program, so let's just do it from here. So I hit play. I have a force that's not changing. The component of the force, by the way, is F cosine theta, right? We see that, right? And I get a horizontal line. This is a force versus displacement graph. And I get a horizontal line. So let's draw that graph and kind of pick it apart a little bit. So I have, and let me do this just to make sure we're all on the same page. This is my force, my applied force. Let me call it FA for applied force. This is my horizontal component of the force, which is the component in the direction of motion. So that's applied force times the cosine of the angle. And then I have this vertical component, which doesn't do work, which is the applied force times the sine of the angle. Right? So FA cosine theta is the one that actually does work. So that's what I'm going to actually plot. I'm going to take my graph, my force versus displacement graph. And we got a horizontal line, right? Got a horizontal line where this is the applied force times the cosine of the angle, and that does not change. It does not change. And let's say that it acted over a certain distance, up to here, certain distance. What could I do with this graph to determine the amount of work done? What could I just measure on this graph in order to determine the amount of work?
The area.
What?
The area.
The area, right? The area here is the component of the force that does the work, which is the height of my rectangle, times the width of the rectangle, which is just the distance d, displacement d. Commutative property of... Oh, come on. It's rough being so popular, you know. So, commutative property of multiplication says I can put the d in front of the cosine theta. So I get the applied force. I'll just put F force times distance or displacement times the cosine of the angle. That's the area. That's this area right here. Well, doesn't that look like an equation that we now know? Isn't that the equation for work? Yeah. So there we go. The area between the force versus displacement graph and the horizontal axis equals the work done. That's just something you need to know. And if you don't know it, you should be able to look at that kind of graph and just mentally say it. Okay?
So you, I was gonna big brain it, but it's all good.
Stop it. Oh, I'm sorry. Yeah. No big brains in here. Up here, anyway.
I was gonna. It's just the integral.
Quiet. I'm actually going to talk about that today
Okay.
because it's interesting. All right, if you look at the front page of the notes that you got for this unit, at the bottom, you have a force versus displacement graph that looks like this. Turn this up now. I have a force versus displacement graph that looks like this. And if this carries over to graphs that aren't horizontal, then I should still be able to say the area here equals the work. However, it does no longer equal an expression that I can write as FD cosine theta. Because the force goes from 0 to some maximum value and then back down to 0 as the object moves from here to here. This is one graph where the horizontal axis is literally the distance that the object travels. Okay? But we can use the area. We can't say, well, the work is just the area. Right? How many joules of work are done? Determine the area, and you're good. If you're like me, this is not... when I was first taught this, I did not like it. I was like, it's easy to see why this gives you work. Because you have a constant force, right? The rectangle, I could see why that should give me the amount of work because it's literally force times displacement. That's work. I look at this. I'm like, there's no rectangle there, right? It's a triangle. There's no rectangle there, so the force changes. Can I be sure that this statement, the area, is going to be the same? Can I be sure that that is going to work here when I have a varying force, whereas it didn't work, or whereas it's obvious that it works here? Okay, that's a struggle that I had when I first learned this until I started learning calculus. And then I realized some things. And so we are going to talk about a little bit about the essence of calculus right now. You don't need to know it for this class, but it will help you whenever you actually start learning calculus, or if you're already learning it, you already know this. But it will, if you're like me, maybe you don't fall in the same camp that I did. I didn't like this. I could see this, obviously, when I first learned it. This, I was like, nah, I have questions about that. I question the validity of that. But whenever I learned that you can actually determine areas under lines that are like curved, and how we actually do that, or approximate those areas at least, then it clicked. Okay. So let's say that I have, this is a force versus time graph. Again, this is the essence of calculus, but you don't have to, you're not going to do it in this class, but it should make it clear why this can actually work, right? The area is the work, no matter what shape the graph makes. Let's say I want to approximate how much work is done. I can't just put the force is varying over the whole time, right? Force varies. Let's say I want to approximate how much work is done here. I want to approximate the work done. Well, an easy way to approximate the area under a curve is just to draw a bunch of rectangles, right? Right? If I find the areas of those rectangles and add them together, I have a rough approximation for the area under the curve. Are we good with that? Each one of those rectangles, let's say this one, has a height What's up?
I should be in here right now.
Sure.
What are you guys doing?
Physics.
I know that.
Work and energy.
Okay, can I see a little bit?
Yeah.
Okay.
This is stuff that they don't need to know. I'm just going to get. Anyway, so the height of this particular rectangle is just the value of the force at that time, right? Right? You with me? The width of that rectangle is just the displacement that the object undergoes under this part of that time. You with me? So if I want to approximate the area under this curve, then I just figure out the areas. Each one of these areas works just like this one. You with me? Is that sinking in?
Yeah.
Each one of these areas gives me an area that I can understand when it comes to work and energy. It's force times displacement. It's the area of a rectangle. Each one of those rectangles works the same way. How can I get a better approximation of that area here? If you're not in calculus.
These triangles.
Well,
It's
using
not like what you do. Like you
you probably mean trapezoids.
Yeah.
Oh, yeah.
But without using trapezoids, what can we do?
Draw smaller rectangles.
Smaller rectangles. Yeah. If I make smaller rectangles here, then they're gonna fit better, right? This rectangle right here would go to there, and then so on, and then I get smaller rectangles. They're gonna fit under the curve better, right? And then eventually, what you learn in calculus is that you can divide this area into an infinite number of rectangles that have infinitesimally small widths, right? An infinite number of rectangles here, each that work just like this. It's a height times a width, gives you the exact area. if you divided this curve, the area under this curve, into an infinite number of infinitesimally thin rectangles and added those areas together, then you figured out the actual exact area. That's calculus, right? That's what you learn next year, or what you're learning right now. Are you guys doing integrals right now? Not yet?
BC is.
Okay. So there's tools. Miss Fudge, one of the best teachers at the school, in my opinion, besides, of course, Mr. Shilley. She's excellent. She will teach you how to do this. And it sounds more complicated when you use words like infinity and infinitesimal. It's not that bad. It's not that bad. We don't do that in this class, but if you understand this, then you understand the struggle that I had when I learned this, when I went from this to that. Does that make sense? Mm-hmm. Okay. So all that being said, I could do the same thing here. I could divide the area under a triangle into a bunch of small rectangles, find the areas of each of those and add them together. But if I wanted the actual exact area, I just find the area of a triangle and I'm good to go. And that area is equal to the work done. You feel it? Feel it? Yeah?
Yeah.
Okay. All right. Is that it for today? Kyle?
Yeah.
No.
That's good.
All right. I'm going to erase all this, okay?
What are we still doing? Force and displacement,
This is work and energy.
or I'm working energy.
Yeah.
Okay, I'm gonna go get my class started. I'm gonna come back.
Okay, sure.
Would you mind letting me in again?
Sure. You can put the doorstop there if you want.
Okay.
What's on the ground? Doorstop.
And kudos.
You got a
this
class
young
to
lady-
teach.
Kudos to this young lady who would not get up, and she didn't want to interrupt your teaching. So.
Figures. Tatum. I'm just kidding. That's a good thing, right? All right. So, bottom line, if you have a force that varies, find the area under the graph, and you're good. Okay? All right. So now we're going to move into something else. This is a more, to me, at least, a more difficult abstract concept to understand. And that is conservative forces. Conservative forces. Now I'm just going to read you a definition, and it's probably not going to make much sense, but then hopefully by the end of the period you'll understand a little more about what it's about. So I'm going to read the definition a few times by the end of the period, and hopefully it'll start to sink in. A force is conservative when the work it does is independent of the path between the object's initial and final positions. So we're talking about work being done on an object. If the force that is doing the work is what we call conservative, then the work that it does is independent of the path that the object actually takes from its starting point to its ending point. Well, it's confusing, right? Very confusing. What you want to understand about conservative forces, though, is that if conservative forces are acting, or if only conservative forces are acting, mechanical energy, which I'll define in a second, will be conserved. Or underlying mechanical energy. You learned about conservation laws last year, right? Conservation of charge, conservation of mass, conservation of energy. Right? These are things that are true. The other day, whenever I showed you that Science Asylum video, underneath it was that video about Emmy Noether. I think you have to say her name. They knew conservation laws existed before her, but they didn't know why. And again, she was a mathematician who just dabbled in physics and figured this out, which is amazing. But she mathematically proved that given certain symmetries in nature, in the universe, those symmetries will lead to conservation laws. She showed that mathematically doing work that I've looked at and have no understanding of because it's way over my head. But she proved it. That's the thing. So mechanical energy, conservation of mechanical energy arises because of certain symmetries in nature. So what is mechanical energy? I'm going to define that. Mechanical energy, which we abbreviate as ME. We will experience 4 types of mechanical energy in this class by the end. But for right now, we just talk about gravitational potential, gravitational potential energy, symbol U subscript G. The equation for it, delta U sub G, or the change in mechanical energy, is mass times the acceleration due to gravity times the change in height. If delta Y is positive, that means final position is greater than our initial position and we gained energy. If delta Y is negative, then our final position is smaller than our initial position. Delta U is negative because we've lost gravitational potential energy. And linear or translational kinetic energy. And that just gets the symbol K on the formula sheet. And the formula for that is K equals 1/2 mv squared. So if, and I'll elaborate for sure, if the forces that are doing work on an object are conservative, then the work they do on the object is independent of the path that the object actually takes. It's real confusing, I know. And so I have a nice simulation that I feel like really illustrates this point better than I could in words. All right, so I got this situation. If I zoom in here and hit play, you'll notice that from this location, I got 3 objects. 3 objects, all of equal mass, are all going to be launched from the same position with the same starting velocity. So they're launched from the same position. If you remember from the Science Asylum video, position tells you about potential energies. Potential energy is the energy associated with position. So if these guys start from the same position, they have the same gravitational potential energy. What's the source of gravity? These 2 things here, stars, planets, whatever you want to think of them as being. They're not going to move. They're not allowed to move in the simulation. And then they also start with the same velocity, so they have the same starting kinetic energy. Which means if they have the same gravitational potential energy and the same kinetic energy, then if the work done on the particles by the gravitational forces from these 2 guys as they move through this space, their energy at if they end up at the same location, their kinetic energy should be the same there, because they should have the same gravitational and kinetic energy if they're at the same location, because the path that they take doesn't matter. The work done by the gravitational force, which is conservative, by the way, that's the first force that we'll learn is conservative. The gravitational force is a conservative force. The work done by it is independent of the path that the objects actually take through the space in which that force is acting. So what we can do to demonstrate that, I hit play, and these 3 guys start moving. And they're taking very different paths, right? They started with the same energy. They started with the same gravitational potential energy. They started with the same kinetic energy. And they end up at certain times at the same locations. So these guys are going to cross right about there. Someone mark that. So at that point, these 2 guys, took different paths to get to the same location, right? Let me read the definition again. A force is conservative when the work it does is independent of the path between the object's initial and final positions. These 2 objects had the same initial and final position. They started here, they ended there. They keep moving, but at that point, they had the same final position. Therefore, the same amount of work should have been done on both. Since they started with the same kinetic energy, they should have the same kinetic energy at that point. And what we'll see is that at that point, this first guy, now this isn't going to be perfect. Again, there's limitations to this program. But at that point, this object has a speed of 1.17 meters per second. We'll call that guy, because he's the middle guy, we'll call that guy object 2. I'll erase this after we're done. So this guy should, if he gets to that point, have that same velocity. It's about the same, 1.16 meters per second. So they end up with the same kinetic energy. It's not the same as when they started with more kinetic energy, but then the gravitational force did work on them as they moved through the space. And since they started the same position, ended at same final position, the work done on both was the same. Okay. So the work, what you say is that the work done is independent of the path taken. Okay. You feel that? And we can further check it because looks like these guys cross almost at the same time, and they pretty much have the same velocity. Right? That just happened by chance. So they both have about 0.99, 0.98 meters per second velocity. So they have the same kinetic energy there. And then goes even further. Eventually these guys both cross the same point down here. Which looks to be right about here. So again, if the work done by the gravitational force in the simulation is independent, oh man, I overshot just a little bit, is independent of the path taken by the objects, they should have had the same amount of work done on them by the gravitational force when they reach that location. And so they should have the same kinetic energy. 0.67 meters per second, this guy has. So the other guy, when he gets there, he should be moving at about 0.67 meters per second. And sure enough, he almost 0.65 meters per second. So almost the same thing. Okay. Does that kind of clear it up a little bit? The path taken by the objects in response to conservative forces doing work does not matter. Another caveat to that, these guys are actually in orbit, by the way. Two of them are in orbit. I noticed after I made it. Orbital mechanics is pretty cool. The energy associated with orbital mechanics, that's something that we'll learn about in AP Physics C a little bit. They're actually in elliptical orbits. Very different from the orbits that we've studied. That guy actually collided. He fell into the star. But notice that sometimes these guys come back to the same location, right? They end up at the same location. And it turns out that when they're moving away in these elliptical orbits, negative work is being done because the gravitational force is constantly this way and they're moving that way. That angle is greater than 90 degrees. So that's negative work. And then they end up turning around. Now it's in the same direction. Now it's positive work. That's why when you're moving away from the sun, like a comet, something with a highly elliptical orbit, they slow down on the way out. And then they speed up on the way in, as you would expect. But from a work energy standpoint, we can look at it like that. Negative work is done on the way out. Positive work is done on the way in. If they end up at the same location, zero net work has been done. Right? Zero net work is done on the whatever's doing the orbiting. And it's a good thing, too. Because if the sun did positive work on the Earth, its kinetic energy would increase, and it would spiral away from the sun, and we'd all freeze. If negative work was done on the Earth by the sun, then it would spiral into the sun, and because it would lose kinetic energy, and it would spiral in, and we'd all burn up. So it's a good thing. And this is kind of like circular motion, right? If it's a perfectly circular orbit, no work is ever done, because the force is always exactly perpendicular to the direction of motion. It's good. This is good stuff. This is high-level stuff, guys. You want to understand it. You want to understand it. Okay. And as a reminder, no food or drink in the classroom. I'm just kidding. I'm kidding. I'm just kidding. Okay. So does that kind of make sense? Okay. Now, if we're talking, and this kind of a situation, we definitely will not deal with in this class, at least the work, because this is very complicated. Now the force is constantly changing, and its direction is constantly changing, and you have the direction of motion constantly changing. So everything about our work equation is changing in this kind of a scenario. And that's when you do third semester college calculus. That's when you're doing line integrals with vectors and stuff like that. And so that's in your future if you're going to be an engineer or a physiker or a chemist or something like that. So situations that we're more likely to see is situations like this. Right? Now, as an object moves horizontally, how much work does gravity do on it? Zero. So if this object moves down the hill, then gravity is really only doing work in the vertical direction. It's not doing any work in the horizontal direction, right? Because gravity points down, it is moving horizontally. Yes, it is slanting downward, but we can change that displacement. We can decompose that displacement vector, this displacement vector, into a vertical component where gravity is doing work in that direction, and a horizontal component where gravity is definitely not doing work. We could say that the normal force is actually doing work kind of in that direction, but we're just worrying about gravity right now because gravity we know is a conservative force at this point. What that means is that on more terrestrial levels like this, when we're not talking about solar systems and things orbiting and stuff like that, we can say, well, the work done by gravity on objects at the surface of the Earth as they move downward is due solely to the initial height and the final height, or the initial vertical position and the final vertical position. Meaning that if there's no friction here, which there isn't because I turned it off, these two objects start from the same height at zero velocity. They should reach the bottom with the same velocity. They start with the same amount of gravitational potential energy. They should end up with the same amount of kinetic energy. They are the same mass, so they should reach the bottom with the same speed. And what we'll see is that is true. Now, obviously, this guy's going to get there faster because he's falling straight down. He's not sliding down a ramp. But they will end up with the same final speeds. So this guy, right when he hits the ground, is moving at 7.68 meters per second. This guy takes a little longer, but by the time he hits the ground, look how fast he's going. 7.6, limitations of the program, but 7.66 meters per second. Same speed. Same speed. So without friction, the path that objects take near the surface of any, usually the Earth, but any planetary body, all that matters when it comes to determining how much work is done on them as they fall by the gravitational force, is the initial height and the final height. So the initial vertical position and the final vertical position. Again, a force is conservative when the work it does is independent of the path taken between the object's initial and final positions. Here we're just talking about vertical positions. We can either take a path that goes straight down, or we can take a path that goes down like this. Or we can take a path like a roller coaster. It goes down, and then up, and then in a loop, and then up a hill, and then back down a hill. We can do all that. And if there's no friction, if there's no air resistance or anything like that, then it just keeps on going forever. Okay?
Wait, Mr. Graham, the masses are the same, right?
Yes.
Okay.
Yes. All right, does that all make sense? You like it? You feeling it, Kurt? You staying awake?
Yeah.
Awesome.
No, I heard them.
Awesome. Okay. How much time do I got?
About 10, 15 minutes.
Oh, sweet. That's plenty of time.
Yeah, 15.
So, let's look at...
It's not 15. We have like 10. We have like 7.
You lied to me. I can't believe you would lie to me.
It's something. You got time.
It's 10:08. Don't you guys know the bell schedule?
No.
Now it's 4:15.
Fourth period ends at 11:03.
Yeah.
This period ends at 10:08. They changed the schedules on us this year. I don't know why.
Don't you wish it was Friday?
You so mine. It is Friday. You got it.
Okay.
Why are you trying to get it? It's not my
So, if only conservative forces act, mechanical energy is conserved. Mechanical energy is gravitational and kinetic energy. Those two together. So if I have a system or an object, let's say I have an object that's sliding down a hill or up a hill. And note that path independent, the hill could be curved. We can still do it because all we care about is where it starts, where it ends. Newton's laws, you can't do that, at least with algebra. That's a hard problem, using Newton's laws to describe a motion that's sliding down a curved incline. With energy, it's super easy, way easier, far easier. And remember, Newton didn't know. Like I talked about the calculus of work and energy. Newton didn't know what energy was. It wasn't a concept when he was alive. It was after he died that they came up with the concept of energy to describe the same types of things, but just usually with a lot more convenience and a lot less hardcore math to deal with. So it's kind of nice. But let's say I have an object like we were just talking about where we have an object starting at a certain location and ending at a certain location, converting energy from one type to another. We could say that that system has an initial amount of mechanical energy. If conservative forces are the only forces acting, then that should equal the final mechanical energy. And until you're really feeling good about this, I would expand this equation out every time into the initial kinetic energy plus the initial gravitational potential energy, so K naught plus UG naught, where you go, equals the final kinetic energy plus the final gravitational potential energy. More often than not, at least one of those is going to be zero. Right? If I have an object that I'm dropping from a certain height, to ground level or to countertop level, it starts with 0 what? Kinetic energy. And it ends with 0. And it ends with 0 potential energy. Starts with 0 kinetic, ends with 0 potential.
But when it hits the ground, it doesn't have any kinetic energy left either.
That's after it hits the ground. That's after another interaction that will do work, non-conservative work.
What about the instant before it hits the ground?
That's how we say it. That's how we say it. When we're doing this stuff, we're talking about not when it hits the ground. We're talking about what its speed is, the infinitesimally small instant before it actually makes contact.
So it keeps does it slowly convert potential to kinetic, or does it?
No, there's a collision there. There's a collision there that we will talk about in our next unit.
No, because it starts at the top with potential, and then immediately, like the instant that it's let go, is it all turned to kinetic at that point, or is it?
That's a great question. That's a great question, Kurt. Thank you. Let me answer that. I might have meant to show this before I went to that next step. So I appreciate that, Kurt. You're not trying. You're just trying to learn, right? Yeah. Okay. Let's take this guy and plot graphically. And this will be with respect to time because we just want to see how the energies evolve over time. Let's plot the kinetic energy, the linear kinetic energy, the potential gravitational energy, and the total energy on the same set of axes. It'll just be time on the horizontal. Okay. So we drop it, we let go. It starts with maximum potential energy, 0 kinetic energy. And then the potential energy should decrease as the kinetic energy increases. And at all times, if the force that's doing the work is conservative, the sum of those two energies should be the same. Right? What's that?
Throughout the entire process.
Throughout the entire process. And so as we see, the kinetic energy is this green one, which is increasing with time. This bottom pink one is the potential energy, which is decreasing symmetrically with the kinetic energy. And then the total energy is this line at the top, which stays completely horizontal for the whole motion. Halfway down, half of it's kinetic, half of it's potential. As it gets lower to the ground, it's more kinetic than potential, right? Potential started out as a maximum. It's about to be 0. Kinetic energy started at 0. It's about to be a maximum. Total energy has stayed the same. And like Kurt pointed out, we're not interested in what happens yet. We're not interested in what happens when it hits the ground. Because now that's an external force. That force will not be conservative. And that force will definitely be, it'll be a collision. We'll study that in our next unit. But, and you'll notice at that time, when that happens, a lot of the energy was lost. Right? Where does that energy go? Does it disappear from the universe?
Probably a little bit when it hits something, right? It transfers the energy to whatever it hits, right?
Yeah. And so what happens on the atomic level, what's happening there is that the atoms come into contact and the atoms jiggle faster than they did before. They vibrate faster. They get hotter. So you get a transfer of thermal energy.
So most things are...
Hopefully you never get in a car crash, but if you have 2 cars ever crash and you touch like the metal that was involved in the collision afterwards, it will be noticeably warmer.
Yeah, it's hot.
Yeah.
It's hot.
You don't see, even here, I dropped this guy on the table, right? That energy that it had here in the form of gravitational potential energy, it's gone now.
Turned into heat.
It's not gone. It's mostly turned into heat. What else does it turn into? I wouldn't recommend that. What else does it turn into? Can you hear?
Yeah,
Turns into sound.
that's also heat, because it's just vibrating the...
Well, I wouldn't call it heat,
Is it,
but it requires.
It's making the air
Well,
vibrate faster.
We'll learn about that in our sound unit.
Isn't that
Well-
hotter?
No, we'll learn about that. It definitely requires energy, though. Sound requires energy to be formed. Yep.
Is that why when you like hit something really hard, your hand will sting or something?
I think that's more of like your body's physiological reaction to stress, and so it pumps chemicals in there, and then.
This thing where they're like trying to figure out if you could cook a turkey by slapping it.
Oh, there's a video that I think it calculates how many times you'd have to slap a turkey to actually cook it. Yeah. Anyway, so yeah, when these two guys come into contact, the atoms involved in the collision start jiggling faster. That's literally what temperature is. It's the average measure of the kinetic energy of the particles in the material. And so they start jiggling faster, they get more heat.
That's what cool.
A roller coaster, when it's going along the track, you put your hand, don't do it, but if you put your hand on the track before the roller coaster goes over it, and then you take your hand off and the roller coaster goes over it, and then you touch it, it'll be noticeably warmer. Because roller coasters start here, but every subsequent hill gets lower and lower. Every subsequent loop gets lower and lower. Because, with no loss of energy, they stay at the same height. They could stay at the same height. But because energy is lost, converted to thermal and sound energy mostly, it loses energy over time. Okay. All right. So there's that. Thank you for bringing that up.
Using that program, it'll solve all our physics problems.
Hello? Oh, no. What did I do?
The energy inside the battery is transferred into the. That's chemical energy.
Chemical energy to electrical energy to... Okay.
No.
Okay, so we can write an equation for this. And in a second, it'll only take a minute, but before that, I forgot to do this. Let's list some conservative forces and some non-conservative forces. Because if you recognize that the forces acting are conservative, then you can use this equation, the conservation of mechanical energy. The main conservative force that we deal with is gravity. Another one that we use quite frequently, second semester, is the electromagnetic. The equations, by the way, that dictate gravitational potential energy and electric potential energy are derived using calculus by using calculus to determine expressions for the work done by those forces, and then that's how we get gravitational potential energy, the big kid version, and the electromagnetic potential energy, the big kid version. We also have spring forces. These are conservative forces, spring, but if it's an ideal spring, which like an ideal gas doesn't actually exist. But we have largely ideal springs. What that means is that here I got this system that has a constant interplay between kinetic, gravitational potential, and spring potential energy, right? You pull a bowstring back, you store energy in it, you let go, it gets converted to kinetic. So if this was an ideal spring, this guy would literally go forever. It would never stop.
But then we have the energy.
Right. But if you look in the spring, at the microscopic level, you have internal friction. It's called spring damping. And that will actually, and you got a little bit of air resistance too, but eventually this comes to a stop because there is internal friction that will take some of this energy and convert it to the heat. The spring itself will actually heat up a little bit. And then you got the strong and the weak nuclear forces, which we don't even touch at all in this class.
And what gives light going?
So that's pretty much. That's beyond the scope of this class. So non-conservative forces are friction. That's the main one. Obviously, if there's friction on the ramp when the object slid down it, that friction would prevent that ball from having the same speed at the bottom as it did when it was just dropped. Right. So obviously, the path is definitely the work done is definitely dependent on the path when it comes to friction forces. Air resistance is non-conservative.
So things that usually stop things are
Yeah, yeah, but also applied forces. Applied forces, and it's easy to see why they're non-conservative because I have my regulation size hockey puck here, and I push it. Its energy is zero, right? Its energy is zero. I push it, and then it has energy. So obviously my applied force is not conservative because mechanical energy was most definitely not conservative.
It's not constant.
Okay. Yeah, so that's pretty much the big three, the most important ones. Now, what I want to do is go back to example 4 on your notes, that last part. Remember when we used Newton's laws to figure out how far this guy would go up the hill? How high it would get?
Yeah.
What was the answer to that problem?
The answer to that problem.
The height was initial velocity squared over 2g. And that required force analysis with Newton's second law, vector decomposition to determine the acceleration, and then use that acceleration with kinematics to determine how far up the ramp it went. Then we had to use SOHCAHTOA trigonometry in order to figure out the height corresponding to that distance up the ramp. Well, let's use conservation of energy to do the same problem. That object starts from the bottom, so it has no potential energy. That object, by the time it came to a stop at the top, has no kinetic energy. So all we do is say my initial kinetic energy, which is 1/2 mv naught squared, equals my final potential energy, which is mg delta y, but in this case, delta y is equal to the height. Yeah. Delta y, delta y is our change in potential energy. Delta y, it's just the height. And many teachers and many formula sheets just define gravitational potential energy as mgh. Everyone brought mass to the party. Multiply, what are we looking for? Height. Multiply both sides by g. I can rewrite the left side as v naught squared over 2, right? Equals gh. Divide both sides by g, or if you're like me, multiply by 1 over g. So you have a fraction multiplication on this side. And you get that the height is v naught squared over 2g. Much easier. Much more efficient, right? Doing it the other way took up half the board up here. This one, some students literally just write this first because they know it was all kinetic, all turn potential, and then solve that here in 2 steps. So take home point there, if confronted with a problem where friction isn't a thing, and you can attack that problem from the standpoint of Newton's laws and kinematics or energy conservation, you probably want to use energy conservation.